let's set up our premise today. We're talking solar panels from 1977 to 1987. And we've kind of already seen with technology, as technology gets better, a lot of times some aspects of it gets cheaper. So I'm guessing solar panels improve with generations of solar panels, just a guess. Check out what's happening to the price. It's going down. It's yelling timber. So you are going to look at this exponential function. You're going to answer the questions. Notice function notation's back. So interpret your function notation. And then for 4, it says, what's the factor? I just want you to write the equation. Okay? In function notation. So you're going to work through this right now with your partners. This could take as little as 5 minutes, maybe 8 to 10.
Situation 2 years after 1977, the dollar per watt was $45.
Okay. So we did 9 years after we did these. I'm just going to summarize. I forgot for the video. 4 years after was like about 28. Is that right? And 3.5 years after was about what? Or do I have those mixed?
29-ish.
3.5 was 29.
Yeah, the other one's 30. 25. 25-ish. There we go. The price is going down. And then what Ryan just said is the price was $45. Right about here, somewhere in there, right? So what time did you get for that, Ryan? Yeah. How many years? 2 years after. The price was $45 per kilowatt. I looked it up today, somewhere between 3 and 4 today. It looks like when I Googled it, unless Google lied. So, last thing I want to do is get a function for this. So, f of t. Help me out, JP.
Equals 80 and then 3/4 hour of whatever.
To t. Since I call it f of t, it needs to be t. How did you get 3/4?
Because it's 60 divided by 80, which is 0.75.
60 divided by 80. I did it different, but the same. I did from 80 to 60, it went down 20. 20 is 1/4 of 80. So in my head, it went faster than this, by the way. I went 1/4 less than all of it is 3/4. But same kind of idea, right? Cool. Now you're educated about solar cells. Not cheap energy. That's why if solar cells were easy and cheap, guess what? It'd be everywhere, right? So the reason that there's more than there used to be, if you want to get into it a little bit, is the technology's gotten better, so it's gotten cheaper. And then there's like legislation to require like certain percentages of power, different places to be solar. So even though it's more expensive, like it has to be purchased, kind of thing. So yeah, there'll probably be more and more solar, I'm going to guess. But I've guessed wrong before too. I said, you want to hear my crazy idea, which also must not be cost effective? My crazy idea is just put springs in all the floors everywhere, and when we walk, the spring transfers energy to something. It costs a lot of money. 2 more situations for you to roll through before we're almost done. We're talking about paper. Maybe the most exciting textile on earth, paper. Okay? It used to be a tree, but now it's not. It doesn't even look like a tree anymore, but it is, okay? You're going to look at thickness from folding, and you're going to look at area left from folding. 2 different things. You're just going to run through ABC and ABCDE with your table partner. You've got all the knowledge you need. Let's do this, guys. Who can tell me what the 500ths represents? Maddie? So starting thickness, right? Not very thick. So we're not going to use graphing technology. Who can tell me how many folds it took to be 1 millimeter? 5. So we're going to say 1 millimeter thickness is equal to 0.05 times 2 to the n. And you're saying if n is 5, it works? Well, here's what I'm going to do. I'm going to do it different. I'm going to do a tally system. I'm going to say it starts at 0.05. That's 1. Then 0.1, 0.2, 0.4, 0.8. What did I do wrong? No. Oh, I doubled it 5 times to get to 1.6. There we go. So, you guys, if you did 0.05 times 2 to the 5th, we get 1.6. If I only did it 4 times, it'd be 0.8. So I need that 5th fold. Sweet. Now, it took 5 to get to 1.6. I need to get to 1 centimeter. 1 centimeter is how many millimeters? 10. So I'm at 1.6 times 2. 3.2 times 2. 6.4 times 2. 12.8. So 3 more. How many times to get to the centimeter? Guys? 8. So we got 5 to get to 1 millimeter. 8 to get to 1 centimeter. I know because I doubled it that many times, correct? That's what I got. If you want a table, not a bad idea to get a table where we do NT. We start at 0.05, and you could do 1 is 0.1, 2 is 0.2, 3 is 0.4, 4 is 0.8, 5 is 1.6, 6 is 3.2, 7 is 6.4, 8 is 12.8. You could have done that. All right, let's talk about this paper in the visible area. I'm going to jump right down to B. All right? So I'm going to say f of n equals, what was my starting size of this paper? 93.5. And what's happening to that area? It's going in half a certain number of times. So, if I fold it in half once, I'm going to do 93.5 divided by 2, which is 46.75. Divide that by 2 again, or times half, either way. 23.375. This actually might be nicer with fractions. Half again. 11.6875. So there's 1, 2, and 3. Here's our function, though, that works for everything. We're not going to do that because it's a waste of time for us. Now, can we do negative values for this situation? No, because you can't unfold something that isn't folded, right? Negative exponents? Yes, but this one isn't, right? How about the previous one? Up here with thickness. Could we have done negative? What about with the solar panels? Could we have done negative exponents with the solar panels?
Yeah, the prices went up.
Well, when did it start? What year? 1977. So as long as they were invented already, we could go back in time with our function. But this sheet of paper, we can't unfold something that isn't folded.
Unfold it into a tree again.
What?
Yeah, well, we can't unfold something that isn't folded. What about A? A is the initial value. Can we start with a negative on our initial value? No, we have to have area of paper. Otherwise, there is no paper. Cool. Next thing, we're going to do a little different than how it was intended. So look out for that. We're going to be looking at cell phones a little bit again. Let's get this set up how I want it. I got to use my camera. So here's the problem. We got lots of problems in here, huh? So here's the problem. What I need from you right now, dang it, I need that problem back.
We don't want problems. We only want solutions.
Let's see if I can get it back. Oh, whoo! I got it back, baby. So, this problem says from 2008 to 2011, worldwide sales of a popular smartphone brand can be modeled with this exponential function. In 2009, about 20.73 million of them were sold. If sales continued to grow exponentially, about how many smartphone brand were sold in 2012? I'm going to let you know. There's not enough info. You might even say we have an info gap. What would you need to know? So talk with your table about it. I'm going to give you 30 seconds. Let's hear it. What's something that you could use to answer this? Sean, give me something.
The growth factor.
Okay, I'll tell you this. I'm not going to give you the growth factor. But that would help you. Yeah. Okay.
How many were sold in 2012?
No, that's what you got to answer.
Well, if you gave me it, I could probably solve it.
What's the only bad answers? No answers or stolen answers?
That was my answer.
But how many were sold in 2008?
If you knew how many were sold in 2008, could you find the growth or decay factor?
Maybe.
Yeah, what other year could you use? 10. So I'm going to say, in 2008, 11.63 million. And I'll give you the other in case you want it. 2010, 39.99 million. You've got enough information. Get after it. So, I chose to use my reference years as 2008, 2009, because they're just smaller numbers. So the first thing I did is, I did this. To identify that the change was 9.1 million. And then I divide that by where it started, which was 11.63. Which gives me this number. Yeah, fun number. But this would not be growth. This is the percent it changed. So what percent's no change?
1.
1, which is 100%. So my growth factor, which is what it asks for, is 1.782459,157.
That's what I think you guys may not have the right answer.
And it started at 11.63.
Maybe a typo.
So that's what I've got down. Now let's see where we're going to slap that 12. Where does that go in there? T. So I'm going to do 11.63 where I started times this growth factor of 1.782459157 to the. Oh wait, not 12 though. Sorry, not 12. It started in 2008. So how many years is that? 4. So fourth power. Now I want somebody. Did anybody else do this by like not using this whole number? Somebody round for me and get the answer as well, and we're going to compare them, okay? Somebody round like 1.78 or 1.8, and then let's see what your answer is compared to mine. So I got something like 117.397 million. Sure. So we're just going to make a little change. Just a tenth. Someone round to 100 for me, too. See what you get.
Oh, I remember.
So we want a tenth on a 100th, and we could do 1,000. We've got a tenth. Who's got the 100th? Someone's got the 100th. You're just going to type the same thing I have already written there, just to the fourth power. Josiah, which one you do?
I just did the whole number.
The whole thing. I could have done this myself already, I think, maybe. Okay, I'm going to start. 11.63 times 1.8 to the fourth. If I do the 1.8, I get 122. If I do 1.78, I get 116.75. What do you notice about these values that I get rounding compared to the answer I got? Are they the same? No, but I only changed one of them by like 0.008. That's hardly a change, right? Why is there such a big difference for hardly a change, do you think? It's exponential. It's because of this. So as we get further and further into things, especially things with exponents, you've seen this with like radius and area of a circle, right? That squared thing, if your radius is a little different, it makes a big difference for area. So just know, I did the whole thing. It's not very practical to do the whole thing. I normally wouldn't, but I saw an opportunity here to show you what things look like with just a little bit of rounding difference, right? It's a big difference because we're talking millions. Millions and millions. Almost 5 million if I round to the 10th. That's a lot because it's exponential.